I wanted to work through a problem that involves the concept, notion of electrical current and involves its relationship to charge and individual charge carriers. So in this problem, we've got a electrolytic cell, and as you might know, that cell is used for driving reactions that would otherwise not occur. So for example, in an electrolytic cell, you can break down water, H2O, into hydrogen oxygen gas. You can also use an electrolytic cell if you put in gold chloride or if you put in silver chloride to do gold plating or silver plating by breaking the gold or silver chloride down into chlorine and gold, silver ions. Anyway, we're told that in this electrolytic cell, 3.25 times 10 to the minus 3 kilograms of gold are deposited on the cathode, the negative terminal of the electrolytic cell, in a period that's 2.78 hours. That's about 10,000 seconds. We're also told that the gold ions carry one electronic unit, plus 1.6 times 10 to the minus 19 coulombs of charge. And what we've got to figure out is the current that's flowing through the electrolytic cell. You see, electrolytic cells are driven by a current. The reactions are being driven by a current, and we're going to figure out how much current on average was used to deposit this amount of gold on the cathode. So let me write down some numbers that we're either told in the problem or that we're going to use in solving the problem. Firstly, the charge on each gold ion is positive 1.6 times 10 to the minus 19 coulombs. I'm calling it E, it's electronic charge. Secondly, the mass of the gold that was deposited, we're told that that is 3.25 times 10 to the minus 3 kilograms. Thirdly, we're going to need this. It's not told us in the problem, but I looked it up. The molar mass of gold. So 1 mole of gold atoms has a mass of 0.197 kilograms. So the molar mass is 0.197 kilograms per mole. And then finally, the other number we'll need here is the number of atoms that there are in a mole. That's Avogadro's number. You know this better than I do. 6.02 times 10 to the 23 atoms per mole. So those are the numbers related to the gold, its mass, its charge, and also what we need to calculate the number of gold atoms that were deposited. Finally, we're also told that the time that the cell ran for was 2.78 hours. I'm going to multiply that by the number of seconds in an hour. I got 10,000 seconds. Okay, so now I'm going to go ahead and solve this problem with this information. I'm going to do it actually in 2 steps. Firstly, I'm going to figure out the amount of charge of gold ions that was deposited on the cathode in this period of time. And then once I know the charge that flowed, during that period of time. I can divide by the interval of time, and that will give me the current that was flowing, the average current that's flowing. So in that part, I'm using the definition of electrical current being the charge that flowed divided by the elapsed time. But let's start with the charge. So I'm just going to call that Q. And the amount of charge that flowed when the gold ions were deposited on the cathode is the number of gold ions, I'm just going to call that lowercase n, times the charge that each gold ion has. Well, I know the electronic charge of the gold ions, but I don't immediately know the number of gold ions. And so let's write down what that will be. We do know the mass, lowercase m, of the number of gold ions. If I was to divide it by the molar mass, that would be the number of moles of gold ions. And then if I was to multiply it by Avogadro's number, that would be the number of gold atoms. So that is the number of gold atoms. And then if I multiply that by the electronic charge, that's the total charge that flowed. All these numbers, lowercase m, uppercase m, Avogadro's number, electronic charge, we've listed them all here. I can just fill them in and compute the result. I was a little naughty. I didn't fill in the units. Perhaps I should have put in the units, but I tried to cram everything on one line. But the units are such that kilograms in the numerator and denominator cancel out. Moles in the numerator and denominator cancel out. And we're just left with the units of coulombs. And that's the number of coulombs of gold ions that we deposited onto that cathode. 1,589 coulombs of gold ions. So now I want to figure out the corresponding electrical current. And that's just a matter of using our definition that the electrical current is the amount of charge that flowed divided by the interval of time over which it flowed. Maybe sometimes we use delta Q for the amount of charge and delta T for the duration in time. I've just written it as Q over T, charge over time. We know the charge now. It's 1,589 coulombs. And we know the time. It was 2.78 hours. That was 10,000 seconds. And so if we divide 1,589 coulombs by 10,000, we're going to get 0.15, I'll just write it 9, coulombs per second, or amps. That's the unit of current. Anyway, that was an example of a problem that at its heart involved the definition of current as the flow of charge in some interval of time, and us calculating a current by dividing an amount of charge by a length of time. Probably the most challenging bit on this problem was to kind of read and understand the question and what we're told in the question, and use that information to calculate the charge of the gold ions that were deposited from the information about the gold ions which was given, which was the mass of gold that was deposited.